On December 19th, something happened that won't occur again in your lifetime, and what makes it almost impossible to believe is that most of the world didn't even notice it was happening. 3i Atlas passed closer to Earth than it ever will again before disappearing into the cosmic darkness forever. For months, you've been hearing whispers about this visitor. You've seen the headlines. You've watched the speculation grow. You've heard scientists use words like anomalous, unprecedented, extraordinary. You've seen congressional hearings discuss it. You've watched normally cautious astronomers choose their words carefully, hedging their statements with unusual precision. And as December 19th approached, one question dominated every conversation, every comment section, every late-night discussion about what we're really looking at up there. What will 3i Atlas do to Earth? Stay with me for the next 15 minutes, because in this video, we're going to walk through exactly what happened during those critical hours when this interstellar traveller made its closest approach to our planet, what scientists observed in real time, what the data is telling us now, and what it all means for our understanding of visitors from beyond our solar system. This isn't speculation anymore. This isn't about what might happen or what could happen. December 19th has come and gone. The flyby is complete. And now, for the first time, we have the complete picture of what really occurred when 3i Atlas came as close to Earth as it ever will. You're about to get the full story, the truth behind the tension, the facts behind the fears, and the revelations that emerge from one of the most watched astronomical events in modern history. Think about what this moment represents. An object that formed around another star, in another part of our galaxy, travelled through the cold emptiness of interstellar space for who knows how long, entered our solar system, and passed through our neighbourhood of space close enough for us to study it, to measure it, to try to understand what it's made of and where it came from. This is only the third confirmed interstellar object we've ever detected. The first, Oumuamua, came and went so fast we barely got a glimpse of it. The second, Borisov, gave us more time but stayed relatively distant. But 3i Atlas, this third visitor, gave us something different. It gave us time. It gave us proximity at certain points in its journey. It gave us behaviour that sparked months of intense observation and debate. You remember when this story started making waves? It was discovered approaching the inner solar system on a trajectory that scientists immediately recognised as hyperbolic, meaning it wasn't gravitationally bound to our sun, meaning it came from somewhere else and would leave to somewhere else. And that alone would have made it fascinating. But then the observations started coming in, and with each new piece of data, the story became stranger. There were the jets, the streams of gas and dust erupting from its surface, which isn't unusual for comets, except these jets were locked, always pointing toward the sun regardless of how the object was rotating. There was the velocity profile, the way it was moving through space with slightly more speed than orbital mechanics alone could explain. There were the brightening events, sudden increases in how much light it reflected that didn't match the predictable patterns of known comets. And perhaps most significantly, there was the attention it received from official channels. When was the last time you saw congressional members asking astronomers to brief them on a comet? When was the last time you saw coordinated observation campaigns involving space agencies, universities, and independent researchers all focusing on a single object moving through our solar system? When was the last time you saw the scientific community this careful about their language, this deliberate in separating what they know from what they're still trying to understand? By the time December approached, 3i Atlas had become more than just another astronomical curiosity. It had become a test case, a moment where our ability to observe, to measure, to understand was going to be put to the ultimate challenge during its closest approach to Earth. And with that attention came something else. It came with concern. It came with questions from people who don't normally follow space news. It came with the kind of tension that builds when something unprecedented is happening and nobody can give you simple answers about what it all means. So as December 19th got closer, as this interstellar visitor continued its approach, you had two parallel streams of human response happening simultaneously. You had the scientific community preparing the most comprehensive observation campaign ever coordinated for an interstellar object, positioning telescopes, scheduling satellite observations, coordinating data collection across time zones and continents, and you had millions of people asking a much simpler, much more primal question. Is this thing dangerous? What's going to happen when it gets here? Maybe you were one of them. Maybe you saw the trajectory maps showing 3i Atlas's path through the inner solar system and wondered what close approach really means. Maybe you read articles about the anomalies and wondered if something that behaves this strangely could pose a threat we don't understand yet. Maybe you saw speculation about what interstellar objects might carry with them, whether radiation from deep space, whether unusual compositions, whether something we haven't even thought to worry about yet. And maybe you told yourself you weren't really concerned, but you still checked the news on December 19th. You still wanted to know what happened. That response, that mixture of curiosity and concern is deeply human. We're pattern recognition machines. We're survival-oriented creatures who have learned over millennia that paying attention to unusual things in our environment is how we stay safe. So when something unusual appears in our cosmic environment, when an object from beyond our solar system passes through our neighborhood exhibiting behavior that even experts call anomalous, it's not irrational to pay attention. It's not foolish to ask questions. It's not paranoid to want clear answers about what's happening and what it means for us. And here's what makes this moment in late December 2025 so significant. We're living in a time when that question, what does it mean for us, can actually be answered with unprecedented precision. We have observation tools that previous generations couldn't have imagined. We have data collection capabilities that can measure everything from an object's rotation rate to its chemical composition from millions of miles away. We have spacecraft positioned throughout the solar system providing multiple angles of observation. We have international cooperation that can coordinate telescope time and data sharing in real time as events unfold. So when December 19th arrived, when 3i Atlas reached its point of closest approach to Earth, we weren't watching blindly, we weren't guessing, we were observing, measuring, recording. And now, in these days immediately following that historic flyby, we have something that rarely comes after months of astronomical tension. We have answers, we have data, we have the truth about what 3i Atlas did and didn't do during those critical hours when it passed through the region of space closest to our planet. Before we go deeper into what really happened, if you've been following the 3i Atlas story with me, if you've been watching this interstellar visitor's journey through our solar system over these past months, if you want to understand the complete truth about what this object did during its closest approach and what it means for our understanding of interstellar visitors, hit that like button right now and drop a comment telling me this. Were you concerned about the December 19th flyby, or were you purely excited about the scientific opportunity? I genuinely want to know, because understanding what we fear versus what we discover teaches us as much about ourselves as it does about the cosmos. Your perspective matters in this conversation. Now let's talk about what really happened when 3i Atlas came to its closest point to Earth, what scientists observed during those hours, what the data tells us now that the moment has passed, and why this flyby might have just changed how we think about interstellar objects forever. And that conversation begins with addressing the fears directly, because you can't understand the relief without first acknowledging the tension. Let's be honest about what was happening in the weeks leading up to December 19th. Let's acknowledge the questions that were being asked, the concerns that were being shared, the worries that were completely understandable given what we were watching unfold. Because here's what you need to understand about fear and rational concern. They often come from the same place, from paying attention to patterns, from noticing when something doesn't fit the expected template, from that voice in your head that says this seems different and I want to understand why. The primary concern that kept surfacing was gravitational. Could an interstellar object, even one relatively small by cosmic standards, affect Earth if it passed close enough? You saw questions about this across social media, in comment sections, in discussions among people who don't normally worry about astronomical events, and that concern comes from a reasonable place. We know that gravity is a universal force. We know that every object with mass exerts gravitational influence on every other object with mass. So when you hear that something from interstellar space is making a close approach to Earth, it's not irrational to wonder whether that approach is close enough to matter gravitationally. Then there was the radiation concern. Interstellar space is not a gentle environment. It's flooded with cosmic radiation, with high-energy particles that have travelled across vast distances. And when you have an object that's been journeying through that environment for potentially millions or billions of years, the question naturally arises, what is it carrying with it? Is there radiation we need to be concerned about? Is there some form of high-energy emission we don't fully understand yet? When 3i Atlas exhibited those sudden brightening events, those moments where it became more visible and reflective, some people wondered whether those were outgassing events, or whether they indicated some other kind of energetic process happening on or within the object. But perhaps the deepest concern, the one that was hardest to articulate but easiest to feel, was about the unknown nature of the anomalies themselves. This is where rational concern blends into something more primal. We had an object exhibiting behaviour that veteran astronomers, people who have studied comets and asteroids for their entire careers, were calling unusual. We had jets that remained locked in orientation toward the Sun even as the object rotated. We had velocity characteristics that suggested acceleration beyond what orbital mechanics and solar gravity alone could account for. We had an object that seemed to be following rules we understood, but with additions we didn't. And when you can't explain something completely, when experts are telling you they're still working to understand the mechanisms behind what they're observing, your mind naturally goes to scenarios. What if the anomalies mean it's not entirely natural? What if there's something about interstellar objects we fundamentally don't understand yet? What if this is our first encounter with something that operates on principles we haven't discovered? Those questions sound dramatic when you write them out, but they're the questions people ask when confronted with genuine mystery. They're the questions that drive both tabloid speculation and serious scientific inquiry, just from different angles and with different methodologies. There was also concern about the targeting perception. When you watched the trajectory diagrams, when you saw how 3i Atlas's path would bring it through the inner solar system, passing relatively near Earth during its closest approach, a part of your brain couldn't help but notice the geometry. It's coming toward us. It's going to pass near us. Is that coincidence? Is that just the random chance of orbital mechanics? Or is there something about Earth, about our planet specifically, that influenced this trajectory? Rationally, you know that space is big and trajectories are complex and coincidences happen all the time on cosmic scales. But emotionally, humans are designed to notice when something approaches. We're wired to pay attention to objects moving in our direction. The velocity excess became another focal point of concern. Scientists kept mentioning that 3i Atlas was moving slightly faster than the Sun's gravity alone would predict at various points in its orbit. They explained it as likely due to outgassing, to jets of material erupting from the surface and providing a tiny rocket effect that boosted its speed incrementally. But that explanation, while scientifically sound, requires you to accept that these incredibly precise observations, these measurements of velocity accurate to fractions of a percentage point, are being thrown off by invisible jets of gas you can't directly observe. It requires trust in models and calculations and assumptions about composition and volatile content. And for people who were already noticing all the other unusual aspects of 3i Atlas, that explanation felt incomplete. Social media amplified all of these concerns. You had sensational headlines suggesting worst-case scenarios. You had speculative videos presenting dramatic interpretations of the observational data. You had comment threads where people shared half-understood astronomy, mixed with genuine anxiety about whether authorities would even tell us if there was a real threat. And while much of that content was overblown, or based on misunderstanding of the science, it reflected real emotional responses to a real situation. An object we don't fully understand was approaching Earth, exhibiting behaviour experts called anomalous, and the flyby date was getting closer. What made the concern more acute was the official attention 3i Atlas received. When government bodies start asking questions about an astronomical object, when you see coordination between space agencies and research institutions at high levels, when you notice that briefings are happening and reports are being prepared, it signals significance. It suggests that people in positions of authority think this matters enough to allocate resources, to demand updates, to track closely. And while that attention is exactly what you want when studying something scientifically important, it also feeds the perception that there might be more to the story than what's being publicly discussed. There was even concern about secondary effects, things that weren't necessarily direct threats, but could still impact Earth in subtle ways. What if the passage of 3i Atlas somehow disturbed other objects in the solar system, altering their orbits slightly in ways that might matter years or decades down the line? What if its trajectory brought it close enough to interact with Earth's magnetosphere in ways we haven't predicted? What if studying it required resources and attention that distracted from other important astronomical monitoring? These were not Hollywood disaster scenarios. These were the kinds of subtle what-if questions that people who actually think about complex systems tend to ask. And underneath all of these specific concerns was a more fundamental anxiety about our place in the cosmos. For most of human history, we've been effectively isolated. The distances between stars are so vast that interstellar travel, or even interstellar influence, seemed like pure science fiction. But with Oumuamua in 2017, with Borisov in 2019, and now with 3i Atlas in 2025, we're confronting a new reality. Our solar system is not sealed off. Objects do pass through. Visitors from other star systems do arrive. And every time one shows up, it's a reminder that we're part of a larger galactic ecosystem we barely understand. That realization is thrilling for some people and deeply unsettling for others. So when you look at the collective concern that built up around the December 19th closest approach, you're not looking at mass hysteria or widespread panic. You're looking at millions of people engaging with a genuinely unprecedented situation and asking the kinds of questions humans always ask when confronted with the unknown. Is this safe? Do we understand what's happening? Are we being told everything? What should I be paying attention to? Those are the questions of a species that's smart enough to recognize mystery and emotionally healthy enough to acknowledge when something makes them uncertain. Your concerns, if you had them, were not foolish. Your questions, if you asked them, were not paranoid. You were responding to a real situation with real unknowns, and that response is part of being human. But now we have something that we didn't have before December 19th. We have the other side of the story. We have what actually happened. And that's where this conversation shifts from acknowledging fear to delivering clarity, from validating concern to providing the answers you've been waiting for. Here's what you need to know first, before anything else, before we dive into the fascinating data and the scientific revelations and the implications for future interstellar visitors. Earth was safe. December 19th came and went. 3i Atlas made its closest approach to our planet, and there was zero threat to Earth at any point during that passage. Not a small threat. Not a theoretical threat that didn't materialize. Zero threat. And I'm not saying that to dismiss your concerns or to suggest the questions weren't worth asking. I'm saying it because it's the truth, and because understanding why it's true is the foundation for everything else we're about to discuss. Let's talk about distance first, because distance is the most important factor in almost every question about whether an astronomical object poses any kind of threat or influence. When we say 3i Atlas made its closest approach to Earth on December 19th, we're using astronomical language where closest is a relative term. The actual distance between 3i Atlas and Earth at that moment of closest approach was still measured in tens of millions of miles. Think about that scale for a moment. The Moon, which orbits Earth, is about 250,000 miles away. The distance between Earth and 3a Atlas at closest approach was more than 100 times farther than the Moon. It was roughly similar to the distance between Earth and the Sun, give or take, depending on the exact geometry of the orbits at that time. That distance matters enormously for every concern that was raised. Gravitational influence. Gravity follows an inverse square law, meaning its strength drops off rapidly with distance. At the distances we're talking about, the gravitational influence of 3i Atlas on Earth was essentially unmeasurable. To put it in perspective, the gravitational pull from 3i Atlas on Earth during closest approach was millions of times weaker than the gravitational pull you feel from the chair you're sitting in right now. It's not that it was small but measurable. It was so far below the threshold of any possible effect that it might as well not exist at all in practical terms. Think of it this way. Imagine you're standing on a beach and someone is flying overhead in an airplane at cruising altitude. Now imagine that airplane is carrying a bucket of water. Does the gravitational pull of that water affect you? Technically, yes, in the sense that all mass exerts gravitational influence. Practically no, in the sense that the effect is so infinitesimally small that it cannot be detected or felt or measured by any instrument sensitive enough to survive in Earth's environment. That's the scale we're talking about with 3i Atlas's gravitational influence on Earth. It existed in theory and was completely irrelevant in practice. The radiation concern, also resolved by distance and by the nature of what 3i Atlas is. It's a comet-like object, meaning it's made primarily of ice, rock, and organic compounds. It's not radioactive in any unusual way. It's not emitting dangerous radiation. As it approaches the Sun, solar heating causes ices to vaporize and create the tail and the jets we observe, but those are normal cometary processes, and any radiation it might be carrying from its long journey through interstellar space, any cosmic ray exposure it's accumulated over eons stays with the object. At the distances involved during Earth closest approach, there was no mechanism for any radiation threat. The Earth's atmosphere shields us from cosmic radiation constantly. The Van Allen radiation belts around Earth trap and deflect charged particles, and 3i Atlas wasn't close enough for any of that to matter anyway. Here's an analogy that might help contextualize the scale. If Earth were a basketball sitting in the center of a basketball court, 3i Atlas at closest approach would be like a grain of sand on the other side of the city. That's the scale of separation we're discussing. Could that grain of sand affect the basketball from across the city? Could it exert gravitational pull? Could it somehow radiate danger across miles of urban landscape? The question almost answers itself when you visualize it at proper scale. But what about the anomalies, the unusual behavior that made 3i Atlas such a focus of attention? Don't those suggest something we don't understand? And couldn't that unknown factor pose unexpected threats? This is where we need to separate fascinating from dangerous, where we need to distinguish between scientifically interesting and existentially concerning. Yes, 3i Atlas exhibits behavior that scientists are still working to fully explain. The sunward-locked jets are unusual. The velocity profile has characteristics that require careful modelling. The brightening events suggest complex processes happening on or beneath the surface, but unusual doesn't mean threatening. Scientifically interesting doesn't translate to dangerous. Think about it from first principles. We're observing an object that is clearly subject to the same laws of physics that govern everything else in the universe. It has mass, it responds to gravity, it follows a trajectory that can be calculated and predicted using orbital mechanics. The fact that it also has some behaviours we're still modelling in detail doesn't suggest it operates outside natural laws. It suggests it's exhibiting natural processes we haven't fully characterised yet. That's not a threat. That's an opportunity to learn. The trajectory itself, the path that brought 3i Atlas through the inner solar system and past Earth, was precisely calculated months in advance. Astronomers knew exactly when closest approach would occur, knew exactly how far away it would be, knew exactly where it was going next. There were no surprises in terms of its path through space. The object was following the trajectory that gravitational calculations predicted it would follow. If there had been any deviation, any change that suggested it was somehow altering course or accelerating in ways that might bring it closer to Earth, that would have been detected immediately. We were watching constantly. Dozens of telescopes were tracking it. The trajectory was stable and predictable. There's also the simple reality of scale to consider. 3i Atlas is estimated to be a few miles across at most. Earth is nearly 8,000 miles in diameter. Even if by some impossible scenario 3i Atlas had been on a collision course with Earth, which it absolutely was not, we're talking about an object that's tiny compared to our planet. Earth has been hit by objects this size before over geological time. It's called the impact record, and while those impacts certainly affect local regions and can have global climate effects, Earth as a planet survives and continues. But we weren't even in that hypothetical scenario. 3i Atlas was never going to hit Earth. Its trajectory took it nowhere near a collision path. What scientists were excited about, what made December 19th so significant, was not that there was any danger. It was that we had an opportunity. We had an interstellar visitor passing close enough that our best instruments could study it in detail, could gather data about its composition and behaviour, could learn things about interstellar objects that we simply cannot learn when they're farther away. Close approach in astronomical terms means close enough to study well, not close enough to threaten. And every prediction that scientists made about what would happen during closest approach came true. They said Earth would be safe. Earth was safe. They said the trajectory would remain stable. The trajectory remained stable. They said we would gather valuable data about the object's composition and rotation and outgassing behaviour. We gathered that data. The December 19th flyby was a textbook example of astronomical prediction meeting observed reality. There were no surprises in terms of threat. There were no unexpected dangers that emerged. It happened exactly as the science said it would happen. So when you look back at the concerns that were raised, at the questions that were asked, at the tension that built as December 19th approached, you can now put them in context with what actually occurred. The concerns were understandable given the unknowns, but the unknowns were about scientific details, not about safety. We didn't know everything about how 3i Atlas's jets work or what causes its velocity variations or why it brightens unexpectedly. But we did know it posed no threat to Earth, and December 19th confirmed that knowledge definitively. You can relax about the flyby. It's done, it's over, and Earth is exactly as it was before, completely unaffected except for the fact that our scientific understanding just got richer. But here's where the story actually gets interesting, because while 3i Atlas didn't threaten Earth, what it did do was give us an unprecedented window into the nature of interstellar visitors, and what scientists observed during those critical hours is reshaping how we think about objects from beyond our solar system. December 19th, 2025, was not just another day in the astronomical calendar, it was a day when telescopes across multiple continents, spacecraft positioned throughout the inner solar system, and coordinated observation networks all focused on a single target simultaneously. This was one of the most comprehensive observation campaigns ever conducted for an interstellar object, and what we captured during those hours is going to fuel scientific papers and analysis for years to come. You need to understand what happened not just in terms of data points, but in terms of what it represents for humanity's ability to study visitors from other star systems. Picture the coordination required to pull this off. You have ground-based telescopes in Hawaii, in Chile, in Australia, in the Canary Islands, each positioned to capture 3I Atlas at different points in Earth's rotation, ensuring continuous coverage as the planet turned. You have space-based observatories free from atmospheric distortion, providing crystal-clear imaging across wavelengths that Earth's atmosphere blocks or distorts. You have professional observatories and serious amateur astronomers, all contributing to a global effort to document every visible detail of this interstellar visitor at its moment of closest approach. This is collaborative science at its finest, and what it produced was a treasure trove of observational data. The first major confirmation that came from the December 19th observations was about rotation. Scientists had been tracking 3I Atlas's rotation rate based on periodic variations in brightness as different sides of the object reflected more or less sunlight. But during closest approach, with better resolution and more frequent observations, they were able to confirm the rotation period with much higher precision. The object is tumbling through space, not spinning on a clean axis like a top, but rotating in a more complex way that suggests it's an irregular shape, that it's been through some chaotic history either in its home system or during its journey through interstellar space. That rotation data tells us about the object's internal structure, about whether it's a solid mass or a loose collection of material held together by weak gravity. Then there were the jets, and this is where things got really fascinating during closest approach. Remember that 3I Atlas has been exhibiting these unusual sunward-locked jets, streams of gas and dust that always seem to point toward the sun regardless of the object's rotation. On December 19th, with enhanced observation capability, scientists were able to study those jets in unprecedented detail. They could see the structure of the outflows, the way material streams away from the nucleus, the distribution of different particle sizes in the tail, and what they observed confirmed that the jets are indeed maintaining their sunward orientation, which continues to be one of the most intriguing aspects of this object's behavior. Understanding why this matters requires thinking about how normal comets work. When a typical comet approaches the sun, solar heating causes ices on the sunlit side to vaporize, creating jets that shoot out from wherever the sun is hitting the surface. As the comet rotates, those jets trace out different directions in space, creating a spiral pattern in the tail. You get a complex, ever-changing structure as the rotation carries hotspots into shadow and new areas into sunlight. But 3I Atlas isn't doing that. Its jets maintain orientation toward the sun, which suggests either that the object has some mechanism for concentrating volatile material in sunward-facing regions, or that its rotation is synchronized with its orientation in a way we don't typically see, or that something else entirely is going on. December 19th gave us the clearest look yet at this phenomenon actually happening. Brightness measurements during closest approach also provided crucial data. Observers recorded how much sunlight 3I Atlas was reflecting, what astronomers call its albedo, and how that changed over the hours of observation. There were moments during the flyby when the object brightened noticeably, just as it had done at various points earlier in its approach to the inner solar system. These brightening events are thought to be caused by sudden releases of volatile material, by what you might think of as explosive outgassing, where pressure builds up beneath the surface and then vents suddenly, exposing fresh ice that reflects more light or increasing the amount of dust in the surrounding area that can scatter sunlight. Each brightening event is a clue about what's happening on and beneath the surface of this visitor. Spectroscopy, the analysis of light split into its component wavelengths, revealed information about composition during closest approach. When sunlight reflects off 3I Atlas, or when material in its jets glows from solar heating, that light carries a signature of what elements and molecules are present. During December 19th observations, scientists were looking for specific spectral lines that would indicate the presence of water vapor, carbon dioxide, organic compounds, and various minerals. The data showed a composition consistent with comets formed in our own solar system, which is actually an important finding. It suggests that the building blocks of planetary systems, the raw materials that coagulate into comets and planets around other stars, may be similar to what we have here. That's a profound realization about the chemical unity of our galaxy. The tail structure of 3I Atlas, visible as a faint smudge extending behind the object, was tracked with particular attention during closest approach. Comet tails are complex things, actually consisting of two components. There's the dust tail, made of small solid particles pushed away from the nucleus by the pressure of sunlight, and there's the ion tail, made of charged particles blown back by the solar wind. By studying the shape and orientation of these tails during the flyby, scientists can infer things about the density and composition of the material being released, and about how the solar wind is interacting with it. December 19th provided some of the best tail observations of the entire apparition. What made these observations especially valuable was the multi-wavelength approach. 3I Atlas was observed not just in visible light, the wavelengths your eyes can see, but across the electromagnetic spectrum. Infrared observations revealed thermal emissions, showing which parts of the object were warmest and how heat was distributed across its surface. Ultraviolet observations caught the glow of gases in the coma, the diffuse cloud of material surrounding the nucleus. Radio observations looked for emissions that might indicate complex organic molecules. Each wavelength range tells you something different about the object's physical state and composition. There was also careful observation of the object's position against the background stars, what astronomers call astrometry. By measuring exactly where 3I Atlas appeared in the sky at precise times, and comparing that to predictions based on orbital models, scientists could check whether the object's trajectory matched expectations or showed any deviations. This is how you detect things like non-gravitational acceleration, those tiny rocket effects from outgassing that we mentioned earlier. The December 19th astrometry was particularly important because closest approach is when any trajectory anomalies would be most apparent and easiest to measure. The sheer volume of imaging that took place during closest approach means that researchers now have time series data, sequences of images showing how 3I Atlas changed over hours and days around December 19th. That temporal data is incredibly valuable for understanding dynamic processes. You can watch jets turn on and off. You can see brightness variations happen in real time. You can track how the tail evolves as new material is released. It's like having a video instead of a snapshot, and video data reveals patterns and changes that single images miss entirely. Amateur astronomers contributed significantly to this observation campaign as well. While they don't have the resolution of major observatories or space telescopes, many serious amateur astronomers have equipment sophisticated enough to capture useful data, especially for things like brightness monitoring and position measurements. The distributed nature of the amateur community means someone somewhere is almost always in darkness with clear skies, providing continuous coverage that no single professional observatory can match. During December 19th, amateur observers around the world added their images and measurements to the collective dataset, enriching the scientific return from this event. What's emerging from all this observational data is a portrait of 3I Atlas at its moment of closest approach that is far more detailed than what we had even days before. We're seeing an object that is active, that is responding to solar heating in dynamic ways, that has internal structure complex enough to create unusual jet behavior, that is tumbling through space with a rotation that reflects a chaotic past. We're seeing something that is simultaneously familiar, it acts like a comet in many ways, and strange, it has characteristics that don't fit standard templates. And here's what's so important about the December 19th observations. They give us a baseline. Now that we have this comprehensive dataset from closest approach, we can compare it to observations from before and after. We can ask whether 3I Atlas changed as it passed near Earth. We can track how its behavior evolves as it continues outward from the Sun. We can test whether the anomalies that made it so interesting persist, or whether they were phase-dependent, tied to specific conditions that existed during certain parts of its orbit. The December 19th flyby isn't just one day of observations, it's an anchor point around which we can organise understanding of this object's entire passage through our solar system. But while ground-based observations and Earth orbit telescopes gave us this incredible data set, there was another source of information about 3I Atlas that provided a completely different perspective, and that perspective came from a spacecraft that was in position to see things no Earth-based instrument possibly could. There's something you need to understand about the Parker Solar Probe observations of 3I Atlas that makes them absolutely unique. While telescopes on and around Earth were watching this interstellar visitor from tens of millions of miles away, Parker was positioned where no human-made object except a handful of solar-observing spacecraft have ever been, close to the Sun, inside the orbit of Mercury, in a position to watch 3I Atlas from an angle, and at a proximity that provided information we simply cannot get from Earth's perspective. What Parker saw in the months leading up to December is reshaping our understanding of how interstellar objects interact with the intense environment near a star. Parker Solar Probe is a NASA mission designed to study the Sun by flying repeatedly through its outer atmosphere, the corona getting closer to our star than any spacecraft in history. It's equipped with instruments that can survive the intense heat and radiation near the Sun, and one of those instruments is WISPER, the Wide-Field Imager for Solar Probe. WISPER is designed to image the solar corona and the solar wind, but it can also see other objects that happen to pass through its field of view, and from October 18 to November 5, 2025, as 3I Atlas made its closest approach to the Sun, its perihelion, Parker, was in position to observe that passage from close range. What makes Parker's perspective so valuable is that it watched 3I Atlas during the most intense phase of its solar system visit. Perihelion, which occurred on October 29, 2025, is when a comet experiences maximum solar heating. This is when outgassing is strongest, when jets are most active, when the interaction between the object and the solar environment is most dramatic, and Parker was there to document it. The images Parker captured show 3I Atlas surrounded by a large coma, that cloud of gas and dust extending outward from the nucleus, with tail structures that were being shaped by both solar radiation pressure and the solar wind. You could see the interplay between light and particle streams from the Sun, and material being released from the visitor, a dynamic dance that reveals physics you can't observe from Earth's distance. One of the key things Parker observations revealed was how the solar wind, that constant stream of charged particles flowing outward from the Sun, interacted with the material around 3I Atlas. When solar wind particles collide with neutral atoms and molecules in a comet's coma, they can strip electrons away, creating ions, charged particles. Those ions are then caught up by the solar wind and swept backward, away from the Sun, creating the ion tail we mentioned earlier. Parker could observe this process happening in real time, could see the boundary where the solar wind encounters the coma and begins to ionize and push back the material. That boundary, called the bow shock in planetary science, is a key feature of how comets interact with the space environment. The WISPER instrument also tracked the dust tail, and from Parker's unique vantage point, the distribution of particle sizes in that tail became apparent. Larger dust particles are less affected by solar radiation pressure and tend to follow trajectories closer to the comet's original orbit. Smaller particles, almost microscopic, are pushed more strongly by sunlight and create the characteristic curved tail that we see extending away from the nucleus. By analysing how the tail's brightness and structure varied with distance from the nucleus, scientists can infer the size distribution of particles being released, which tells you about the surface properties and internal composition of the object. But Parker's observations in October and November were only part of the story. Another critical piece of data came from X-ray observations conducted in the days immediately surrounding December 19th. X-ray astronomy is a specialised field because Earth's atmosphere blocks most X-rays from space, so you need space-based X-ray telescopes to observe in these high-energy wavelengths. Several X-ray observatories were tasked with looking at 3I Atlas during closest approach, and what they were searching for was X-ray emission from the interaction between solar wind ions and the comet's coma. Here's how that works. When high-energy ions from the solar wind, things like highly charged oxygen or carbon ions, collide with neutral atoms in the comet's coma, they can capture electrons from those neutral atoms in a process called charge exchange. When that happens, the ion drops down to a lower energy state and emits an X-ray photon. It's a signature of the collision, a way to see the interaction between solar wind and comet material happening in real time. By observing 3I Atlas in X-rays, scientists were essentially watching the solar wind slam into the cloud of gas around the object and leave these high-energy traces of the collision. The X-ray data released around December 18th and 19th showed that 3I Atlas was indeed producing X-rays through this charge exchange process, confirming that it has an extensive coma and that solar wind is penetrating that coma and interacting with the gas there. But the X-ray observations also revealed something about the composition of that gas. Different molecules and atoms produce slightly different X-ray signatures depending on their energy levels and charge states. By analysing the spectrum of X-ray emission, by looking at what energies the X-rays have, you can infer what kinds of atoms are present in the coma. The data suggested a composition rich in water vapour, carbon monoxide, and other volatile compounds, consistent with what we see in comets from our own solar system, but providing confirmation that this interstellar visitor shares that basic chemical makeup. What's particularly interesting about combining Parker's observations from perihelion with the X-ray data from closest approach to Earth is that you get a before and after picture of the object's activity level. At perihelion in October-November, 3I Atlas was experiencing maximum solar heating and maximum outgassing. By December 19th, it had moved farther from the Sun and was cooling down. Comparing the activity level, the brightness of the coma, the intensity of the jets, the X-ray emission strength between these two periods tells you how quickly the object is responding to changing solar input. That response time depends on things like thermal conductivity, how fast heat penetrates beneath the surface, and volatile content, how much ice is available to vaporize. It's another way to probe the internal structure without being able to land on the object or sample it directly. Parker's observations also contributed to the ongoing puzzle of the velocity anomaly. By watching 3I Atlas from a different angle than Earth-based observers, by tracking its motion against the background stars from Parker's position near the Sun, scientists got additional astrometry that helps constrain the object's trajectory and any non-gravitational accelerations. When you have observations from multiple widely separated viewpoints, you can do better orbital determination than with observations from just one location. That improved trajectory modelling is essential for understanding whether the velocity characteristics of 3I Atlas are fully explained by outgassing or whether there's something additional going on. The thermal emission data from Parker's instruments also revealed patterns in how 3I Atlas's surface temperature varied. As the object rotates and different areas are exposed to sunlight, those areas heat up and radiate infrared energy. By mapping that thermal emission, you can infer things about the surface's thermal properties, about whether it's covered in fluffy dust that insulates the interior, or whether there are icy patches that reflect more light and absorb less heat. Those surface properties influence how the object outgasses, how jets form, and how much non-gravitational acceleration occurs. It all connects back to the broader question of why 3I Atlas behaves the way it does. One of the profound realizations that came from Parker's close in observations is just how much we're still learning about comets in general, not just interstellar ones. Every comet is different. Each has its own quirks based on its composition, its structure, its history. But by studying 3I Atlas at such close range and with such advanced instruments, we're seeing processes that are hard to detect in more distant observations. We're seeing how solar heating drives activity, how jets modulate in response to rotation and surface features, how the space environment near the Sun affects volatiles. That knowledge applies not just to this one interstellar visitor, but to our broader understanding of cometary science. The combination of Parker Solar Probe's perihelion observations and the X-ray data from closest approach created a multi-phase portrait of 3I Atlas during its most active period. We saw it up close near the Sun when it was being blasted by maximum radiation and particle flow. We saw it a few weeks later from Earth's vicinity, still active but cooling, its outgassing decreasing as solar input dropped. That sequence of observations is like watching a story unfold, seeing how this interstellar traveller responded to its journey through the hottest part of our solar system, and then began to quiet down as it headed back toward the outer system and eventually back to interstellar space. But for all the data that Parker and X-ray telescopes provided, for all the insights about activity and composition and solar interaction, there were still aspects of 3I Atlas's behaviour that remained puzzling after December 19th, aspects that we've been tracking for months, and that the closest approach observations allow us to update and reassess. Here's the question that everyone following this story has been waiting to have answered. Now that December 19th has passed, now that we have observations from closest approach and the days immediately following, what is the status of the anomalies? Is the sunward jet lock still happening? Are the velocity variations still present? Did anything change about 3I Atlas's behaviour as a result of passing near Earth? Or is it continuing on its trajectory exhibiting the same unusual characteristics that made it so fascinating in the first place? The answer to that question is both satisfying and frustratingly incomplete, which is exactly what you should expect from real science addressing genuinely complex phenomena. Let's start with what we can say with confidence based on post-flyby observations. The the sunward jet lock, that tendency for 3i Atlas's outgassing jets to maintain orientation toward the Sun despite the object's rotation, appears to be persisting even after closest approach to Earth. Observations in the days following December 19th show that the jets are still primarily directed sunward, still exhibiting that unusual stability that has been one of the defining characteristics of this object since the anomaly was first identified. That persistence is significant because it rules out some of the simpler explanations that scientists had considered. If the jet behavior was purely a result of temporary surface features or transient thermal conditions, you might expect it to change as the object's orientation and distance from the Sun evolved. But it's not changing, or at least not changing in ways that eliminate the fundamental puzzle. What does this tell us? It suggests that whatever mechanism is producing the sunward jet lock is either deeply embedded in the object's structure and composition, or is being driven by some process that remains stable across different phases of the orbit. Some researchers are focusing on models where the object has internal layering, where volatile material is concentrated in regions beneath the surface in ways that channel outgassing towards sunward-facing areas regardless of how the surface rotates. Others are looking at thermal models where the way heat conducts through the object's interior creates hotspots that migrate to follow solar heating, with enough efficiency that jets form preferentially in those locations. Both approaches are trying to explain observed behavior with natural physical processes, but both require assumptions about internal structure that we can't directly verify without visiting the object. The velocity profile of 3i Atlas post-flyby is another area where we have updates but not complete closure. As the object moves away from the Sun and away from Earth, its speed relative to the Sun is being tracked continuously through astrometry. What scientists are looking for is whether the excess velocity, that slight surplus of speed beyond what pure gravitational acceleration would predict, remains consistent or changes as outgassing decreases. Initial post-flyby data suggests that the velocity excess is still present, but may be decreasing slightly as the object cools and activity diminishes. That would be consistent with outgassing being the primary cause of the excess, a sort of rocket effect that's strongest when the object is most active and weakens as it cools. However, there's a subtlety here that makes the velocity analysis complicated. Outgassing doesn't stop instantly when a comet moves away from the Sun. Thermal inertia means that the interior of the object remains warm for weeks or months after perihelion, continuing to release volatiles even as surface activity becomes less dramatic. So the fact that we're still seeing velocity excess in late December doesn't immediately prove or disprove the outgassing explanation. We need months of continued observations as 3i Atlas moves farther out and cools more completely to see whether the velocity excess drops to zero or persists at some baseline level. That long-term trajectory monitoring is ongoing, and it will be one of the key datasets for resolving this particular anomaly. The brightening events that characterized much of 3i Atlas's approach to the inner solar system have become less frequent in the immediate aftermath of closest approach. That's expected because brightening events are thought to be caused by sudden outgassing, by explosive venting of volatile material, which happens most readily when solar heating is intense and when there's a lot of thermal energy penetrating the object's interior. As 3i Atlas moves away from both Earth and the Sun, as solar input decreases and the object cools, the conditions for these explosive events become less favourable. So the fact that we're seeing fewer brightening events post-flyby is actually evidence that those events are temperature-dependent and solar-driven, which is reassuring in the sense that it fits natural comet behaviour. But here's where the scientific conversation gets interesting, and where you see the tension between different interpretations of the data. Some researchers look at all of these observations and say, yes, these are unusual characteristics, but they're all explainable within the framework of natural cometary science. We just need better models and more detailed understanding of 3i Atlas's specific composition and structure. Other researchers look at the same data and say the combination of unusual features, the specific way they persist and interrelate, pushes this object into a category that demands we consider whether we're missing something fundamental about what's happening. Both perspectives are represented in the scientific literature, both are argued with evidence and analysis, and both deserve to be taken seriously. This is Steelmanning at its finest, understanding that smart, qualified people can look at the same observations and reach different conclusions about how to interpret them. It's not that one group is being credulous and the other skeptical, it's that interpreting astronomical data, especially for unique objects we can't examine up close, involves making judgments about which models are most plausible, which assumptions are most reasonable, which anomalies require extraordinary explanations and which can be accommodated within existing frameworks. Those judgments are informed by years of experience studying comets and asteroids, and by philosophical positions about how science should respond to outlier observations. The post-flyby period is also crucial for ruling out some of the more exotic speculation about 3I Atlas. If this object were somehow artificial, if it were a probe or a light sail or any kind of manufactured object, you might expect its behavior to change in response to passing near a planet. You might expect course corrections or signaling attempts or activation of dormant systems. The fact that 3I Atlas continued on its predictable trajectory, that it exhibited no behaviors inconsistent with a natural comet responding to solar heating and gravitational forces, is significant. It's not proof that nothing unusual is happening, but it's evidence that whatever is happening operates within natural laws and doesn't involve intelligent intervention or technological mechanisms. Observations planned for the coming weeks and months will continue to track 3I Atlas as it recedes from the inner solar system. Scientists want to see how long the jets remain active, how quickly brightness decreases as outgassing diminishes, whether there are any late-stage brightening events or other activity as the object reaches different temperature regimes. They want to continue astrometry to refine the trajectory and see whether velocity excess truly correlates with activity level. They want to track the tail structure to see how dust dynamics evolve as the object moves into the outer solar system, where solar radiation pressure weakens. Every observation adds another data point to the overall picture. There's also the question of what happens when 3I Atlas moves beyond the range where we can observe it effectively. At some point, probably within the next year or two, depending on how dark it becomes as activity ceases, the object will fade beyond the detection limits of even our most powerful telescopes. At that point, we'll lose the ability to track it directly. It will still be out there, still following its hyperbolic trajectory out of the solar system and back into interstellar space, but it will be invisible to us. The observations we're making now, in these months following closest approach while we still have clear views of it, represent our last opportunity to study this particular interstellar visitor. That urgency is part of what drives the intensive observation campaign. The anomaly discussion is ongoing, and that's not a failure of science, it's how science works when dealing with genuinely novel observations. We're watching the process of hypothesis testing and model refinement happen in real time. We're seeing how the community debates interpretation, proposes explanations, and uses new data to test those explanations. Some anomalies may be resolved as models improve and as we get longer observation baselines. Others may persist as genuine mysteries that will inform how we think about interstellar objects for decades to come. Either way, the December 19th flyby gave us crucial data that will shape that ongoing conversation. But there was another aspect of the observation campaign surrounding closest approach that specifically addressed one of the more speculative questions about 3I Atlas, and that was the question of whether this object might be transmitting any kind of signals, whether there was any indication of technology or intelligence associated with its passage through our solar system. Let's talk about the SETI observations of 3I Atlas, because this is where science meets speculation head-on, where rational inquiry addresses questions that sound like science fiction, and where the results matter regardless of whether you think this object is a natural comet or something more exotic. SETI, the Search for Extraterrestrial Intelligence, is a scientific program that uses radio and optical telescopes to search for signs of technological activity from other civilizations. And breakthrough. Listen, one of the most well-funded and comprehensive SETI initiatives, turned its attention to 3I Atlas during the December 19th closest approach, specifically to ask whether there were any artificial signals associated with this interstellar visitor. Here's why that matters, even if you're confident 3I Atlas is natural. We now live in an era where we know interstellar objects do pass through our solar system. Oumuamua, Borisov, and now 3I Atlas have proven that visitors from other star systems arrive regularly on astronomical timescales. And if another civilization wanted to study our solar system, if they wanted to send a probe to observe Earth or the Sun or any other target of interest, wrapping that probe in ice and rock to look like a comet would be an effective camouflage. It would pass through most observation networks without triggering alarms because it looks like a natural object. So checking whether interstellar visitors are transmitting signals or exhibiting technological signatures is not paranoia. It's prudent due diligence. Breakthrough. LISTEN used radio telescopes to observe 3I Atlas across a wide range of frequencies, searching for narrowband signals that would indicate artificial origin. Natural cosmic radio emissions are generally broadband, spread across wide frequency ranges, because they're produced by random processes like thermal radiation or synchrotron emission from charged particles in magnetic fields. But an artificial transmitter, the kind you'd use for communication, or for beaconing, or for any kind of deliberate signaling, produces narrowband emissions concentrated at specific frequencies. That's how you design efficient transmitters, by putting your power into narrow frequency channels, where receivers can detect it above background noise. The observations were conducted during closest approach, when 3i Atlas was as near to Earth as it would ever be, maximizing the signal strength of any transmission. They covered frequency ranges from about 1 GHz to several gigahertz, the same part of the radio spectrum used for things like cell phone communications and satellite transmissions on Earth. These frequencies are interesting from a SETI perspective because Earth's atmosphere is relatively transparent to them, because they pass through interstellar space without being absorbed or scattered too much, and because they are a logical choice for any civilization trying to make itself detectable. The results of the Breakthrough Listen observations were released in the days following December 19th, and the conclusion was clear. No narrowband radio signals of artificial origin were detected coming from 3i Atlas. The object is radio quiet in the sense that it's not transmitting any deliberate signals that we can recognize with current detection methods. That's an important finding, and it should be interpreted carefully for what it does and doesn't tell us. What it does tell us is that if 3i Atlas is anything other than a natural comet, it's not broadcasting in ways that we know how to detect. It's not sending out a beacon on standard radio frequencies. It's not transmitting telemetry or commands, or any kind of radio frequency signal that stands out from the cosmic background. For people who are speculating that this object might be an alien probe, the SETI results are evidence against that hypothesis, though not absolute proof, because you can imagine scenarios where a probe is inactive, or transmits in ways we're not looking for, or uses communication methods we haven't thought of yet. What it doesn't tell us is that SETI observations can rule out all possible forms of artificial origin. This is the difference between absence of evidence and evidence of absence, a distinction that matters when you're making claims about unknowns. We looked for radio signals in certain frequency ranges using certain search methods, and we didn't find any. That's absence of evidence for radio transmissions. But it's not evidence of absence for the broader question of whether anything artificial could be associated with this object. Maybe there's a dormant probe that's not currently transmitting. Maybe there's technology that uses communication methods outside radio frequencies. Maybe artificial objects don't broadcast at all when passing through other star systems. The SETI results narrow the possibilities, but they don't answer every hypothetical. This is how science approaches extraordinary claims. You design tests that can detect predicted signatures. You conduct those tests with rigorous methodology. You report results transparently regardless of what you find. And you interpret those results in the context of what you actually tested. Breakthrough. Listen tested for radio signals, found none, and reported that clearly. They didn't claim to have proven 3i Atlas is natural. They claimed to have found no evidence of artificial radio transmission. That's precise, honest, and scientifically appropriate. The broader SETI community views observations like this as setting precedent for how we should approach interstellar objects in the future. The protocol that Breakthrough Listen followed, coordinating observation during closest approach, searching across relevant frequency ranges, using sensitive equipment capable of detecting even weak signals, that protocol is now established for future interstellar visitors. When the next Oumuamua, or Borisov or 3i Atlas arrives, we'll know to task SETI instruments to observe it, to check for signals, to add that layer of analysis to the overall study of the object. It becomes part of the standard toolkit for characterizing interstellar visitors. There were also optical SETI observations conducted, looking for laser pulses or other optical signals that might be used for communication or signaling. Optical CT is based on the idea that laser technology is probably universal, that any civilization capable of interstellar probes would also be capable of producing intense, narrowband optical signals that could be detected across astronomical distances. The optical observations of 3i Atlas also returned negative results. No unusual laser pulses, no modulated light that would indicate deliberate signaling, nothing that stood out from the expected reflected sunlight and thermal emission. The combination of radio and optical SETI results gives us confidence that 3i Atlas is not actively transmitting in ways we can detect with current methods. That's a valuable data point. It doesn't close the book on every possible question about this object, but it addresses one specific hypothesis directly and with clear results. And it allows the conversation to shift from speculation about artificial signals to deeper questions about the natural processes that could produce the observed anomalies. What the SETI observations also demonstrate is how seriously the scientific community takes the possibility, however remote, that interstellar visitors could be more than just rocks and ice. The fact that resources were allocated to conduct these observations, that telescope time was granted, that results are being published and discussed, shows that SETI is not a fringe activity but a legitimate scientific pursuit. We're in an era where the search for evidence of other intelligences is conducted with the same rigour and methodology as any other branch of astronomy. And that's appropriate given that the discovery of extraterrestrial intelligence would be among the most profound events in human history. For those who hoped SETI might detect something unusual from 3i Atlas, the negative results might feel disappointing, but science isn't about finding what we hope to find. It's about discovering what's actually true. And the truth that emerged from the SETI observations is that this interstellar visitor is not broadcasting signals in ways we can detect. That truth narrows the space of possibilities and allows us to focus on the genuinely mysterious aspects of 3i Atlas, the velocity characteristics and jet behaviours and brightening events, without the distraction of signal speculation. It clears the deck for rigorous analysis of what we do observe rather than speculation about what we hope to observe. So where does this leave us as we close out the story of 3i Atlas's passage through our inner solar system, as we watch it recede back toward the outer reaches and eventually toward interstellar space again? What have we learned? What does this visitor's brief time in our neighbourhood mean for how we think about interstellar objects and about our place in a galaxy where such objects travel between stars? Right now, as you're hearing these words, 3i Atlas is moving away from us. It's receding from both Earth and the Sun, following the hyperbolic trajectory that brought it into our solar system and that will carry it back out into interstellar space. Its speed relative to the Sun is several tens of miles per second, fast enough that it will escape the Sun's gravitational influence completely and return to the vast emptiness between stars. Within a few years it will pass beyond the orbit of Pluto, beyond the Kuiper belt where distant icy bodies orbit in the outer darkness, and into the region where the Sun's influence fades into the background of the galaxy. And then, decades, or centuries from now, depending on exactly where it's headed, it will be truly back in interstellar space, travelling through the region between star systems where it may have spent millions of years before entering our solar system. We will never see 3i Atlas again. That's not speculation or pessimism, that's orbital mechanics. Its trajectory is hyperbolic, meaning it's not bound to the Sun, meaning it won't orbit back around for another pass. This was a one-time visit. We had these months from its discovery through its perihelion and closest approach to Earth to study it, to observe it, to gather every piece of data our instruments could capture. And now it's leaving, fading as it moves farther away, becoming harder to observe as distance increases and as outgassing decreases and its brightness drops. Eventually, probably within a year or two, it will become so faint that even our largest telescopes won't be able to detect it. At that point, 3i Atlas transitions from observed object to historical record, from something we're actively studying to something we studied. That finality is poignant when you think about it. We shared space with a traveller from another star system. For a brief window in cosmic time, a visitor from the galaxy at large passed through our neighbourhood, and we were here to witness it, to point our instruments at it, to try to understand what it is and where it came from. And then it leaves, heading back into the darkness, and we return to our corner of space where visitors from other stars are rare enough that each one is a historic event. It's like meeting someone on a long journey, sharing part of the road, learning what you can about each other, and then watching them continue on their path while you continue on yours, knowing you'll never meet again. But while 3i Atlas is leaving physically, the data it gave us remains. The observations from Parker Solar Probe, from X-ray telescopes, from ground-based observatories around the world, from amateur astronomers and professional researchers, all of that information is now part of the scientific record. Terabytes of images, spectra, photometry, astrometry, data that will be analysed for years to come as researchers write papers, test models, refine theories about interstellar object behaviour. The legacy of 3i Atlas is not just that it passed through our system. The legacy is what we learned from watching it pass. And what did we learn? We learned that interstellar objects can exhibit behavior that challenges our existing models. We learned that the range of comet activity is broader than we thought, that objects from other star systems might operate on variations of the physics we understand, but with details we're still working out. We learned that coordinated observation campaigns can gather extraordinary amounts of data when the scientific community focuses resources on a single target. We learned that public interest in these visitors is intense, that people care about what's moving through our cosmic neighborhood, that astronomy can capture imagination in ways that translate to engagement and curiosity. We also learned about our own capabilities and limitations. We learned that our observational tools are incredibly powerful, that we can track an object millions of miles away with precision, that we can measure its composition and rotation and outgassing in remarkable detail. But we also learned that there are limits to what we can determine from a distance, that some questions about internal structure and formation history and the specific mechanisms driving unusual behavior require closer proximity than we currently have the capability to achieve. This gap between what we can observe and what we want to understand is one of the driving forces behind proposals for interstellar object intercept missions, for sending spacecraft to rendezvous with the next visitor and study it up close. The scientific community is already discussing what we'll do differently when the next interstellar object arrives, and make no mistake, there will be a next one. Oumuamua taught us that interstellar visitors exist. Borisov taught us they arrive regularly enough that we should expect more. 3i Atlas taught us they can exhibit complex behavior worth studying intensively. The next one will teach us something new, and we'll be better prepared because of what we learned from the first three. There are dedicated survey telescopes to detect interstellar objects earlier, giving us more time to study them before they pass through and leave. There are discussions about rapid response protocols to mobilize observation resources immediately when a new visitor is detected. There are discussions about spacecraft concepts that could be launched on short notice to intercept interstellar objects while they're still in the observable part of their trajectory. The anomalies that 3i Atlas exhibited, the questions that remain even after closest approach, those will drive research for years. Some astronomers will focus on building better thermal models to explain the sunward jet lock. Others will work on compositional models to understand what mixture of ices and organics and minerals could produce the observed behavior. Still others will tackle the velocity problem, refining calculations of non-gravitational acceleration, and looking for ways to test whether outgassing fully explains the excess speed. Each of these research directions is legitimate. Each will contribute to our broader understanding, and together they represent the scientific process working exactly as it should. Multiple approaches to complex questions gradually converging on truth. There's also a philosophical dimension to what 3i Atlas represents. This object came from another star system. It formed in a disk of gas and dust orbiting a star that is not our Sun. It was ejected from that system through some gravitational interaction, maybe a close encounter with a planet, maybe the chaotic early evolution of its home system. It travelled through interstellar space, through the incomprehensible emptiness between stars for timescales we can only estimate. And then it happened to pass close enough to our solar system that the Sun's gravity bent its trajectory and pulled it through the inner system where we could see it. That chain of events, from formation around another star to detection by humans, is a thread connecting us to the broader galaxy in ways that feel almost personal. Every object in our solar system, every planet and moon and asteroid and comet formed here. They're part of our local family, sharing a common origin in the disk that surrounded the infant Sun. But interstellar visitors like 3i Atlas are different. They're from out there, from the galaxy beyond our solar system, and they carry with them information about other places, other star systems, other corners of space that we cannot visit with current technology. They're messengers in a sense, even if unintentional ones, bringing data about galactic conditions and planetary formation processes and the diversity of objects that exist across the Milky Way. Studying them is the closest we can currently come to exploring other star systems directly. And so, as 3i Atlas recedes, as it fades from view and returns to the interstellar medium from which it came, we're left with questions and data and a renewed appreciation for the dynamic nature of our cosmic environment. Space is not empty. Objects move through it. Visitors arrive, and each one gives us a chance to learn something new about the universe we inhabit. The December 19th closest approach was a moment in that ongoing story, a chapter where we focused our attention and our instruments on one particular traveller and extracted every bit of understanding we could from the brief time it spent in observable range. Your participation in this story, the fact that you watched and wondered and asked questions, matters too. Science is not just what happens in observatories and laboratories, it's also what happens in the conversations and curiosity and engagement of people who care about understanding the world and the cosmos around them. The interest that 3i Atlas generated, the discussions it sparked, the way it captured imagination, those are part of its legacy, as much as the scientific papers and data archives. We're living in an era where ordinary people can follow extraordinary astronomical events in real time, where you can watch an interstellar visitor pass through our system and understand what's happening and why it matters. That democratization of cosmic knowledge is one of the great achievements of our time. So here's where we are as this story closes. 3i Atlas passed closest to Earth on December 19th, 2025, at a safe distance that posed no threat to our planet. Scientists observed it intensively, gathering data about its composition, behaviour and characteristics. The anomalies that made it fascinating persist in some forms and have been contextualised by new observations in others. SETI observations found no evidence of artificial signals, and now the object is departing, heading back to interstellar space, leaving behind a wealth of information and a set of questions that will drive research for years to come. It was here, we saw it, we studied it, and now it's gone. But what we learned remains, and that knowledge is how humanity grows its understanding of the universe, one visitor, one observation, one question at a time.